Hello friends, today let us study RLC parallel circuits and parallel resonance. Now in a parallel RLC circuit, the resistor, inductor and capacitor are connected in parallel to each other across a common voltage supply. The circuit thus obtained is called a parallel RLC circuit. Now for the analysis of a parallel RLC circuit, we can see that the voltage supply is common to all three components and the current Is gets divided into IR, IL and IC. There is three components. And hence the current flowing through each branch would be different. And the total current would be the mathematical sum of IR, IL and IC, that is Is. Now since the voltage is common to all three components, the vector diagram will have the voltage vector as the reference with the three current vectors for IR, IL and IC being plotted with respect to this reference of voltage. Therefore, we'll have to find the supply current Is as the phasor sum of the three component currents combined together vectorially. If you remember, we had found Vs as the phasor sum of the three component vectors combined vectorially in RLC series circuit. Here we'll be finding Is, that is the supply current, as the phasor sum of the three component currents combined together. Now applying KCL at node A to the circuit shown here, we get Is minus IR minus IL minus IC equal to 0. Now Is minus IR is replaced by V by R, IL is 1 by L integration of V dt, and IC is equal to C dV by dt. Now for this parallel circuit, the phasor diagram is as shown here. Now IC, that is the capacitive current, will lead the voltage by 90 degree and the inductive current IL would lag the voltage by 90 degree. And Is would depend upon the magnitudes of IC and IL. If IL is greater than IC, it would be downward, and if IC is greater than IL, Is would be upward. Now Is can be found out to be IL minus IC plus IR, which is the vector sum, and the right angle triangle that is formed here is known as the current triangle, and Is can be found out by Pythagoras theorem as Is square is equal to IR square plus IL minus IC the whole square. Therefore Is comes out to be root over IR square plus IL minus IC the whole square. And substituting IR, IL and IC is V by R, V by XL and V by XC, we get Is is equal to V by Z. And here R is equal to V by IR, XL is equal to V by IL, XC is equal to V by IC, and Z comes out to be I 1 upon the root over 1 by R the whole square plus 1 upon XL minus 1 upon XC the whole square. Now 1 upon Z is equal to root over 1 by R square plus 1 by XL minus 1 by XC the whole square. Now this component 1 by Z looks easier to compute than the actual value of Z. So in parallel AC circuits, it is more convenient to use admittance, which is denoted by the symbol Y, to solve complex branch impedances, especially when two or more parallel branch impedances are involved. The reciprocal of resistance is called conductance and the reciprocal of reactance is called susceptance. and obviously the reciprocal of impedance is called admittance. And now the total admittance is the sum of the admittances of each parallel branch, where the admittance y1 would be 1 upon z1, admittance y2 would be 1 upon z2, and so on. Here we can see that the impedance triangle and the admittance triangle both have been drawn. Here, as we have seen before, R is replaced by resistance is replaced by conductance, that is 1 by R. Reactance is replaced by susceptance, that is 1 by X, and Z is replaced by Y, where Y is equal to 1 by Z. And this is the admittance triangle. Now here Y is equal to G squared plus BL minus BC the whole square. Since B is the susceptance of both capacitor and inductor, and here Y is equal to 1 by Z, G is equal to 1 by R, BL is equal to 1 by omega L, and BC is equal to omega C. Now admittance comes out to be root of 1 by R square plus 1 by omega L minus omega C the whole square. Hence impedance comes out to be 1 upon Y, that is 1 upon root over 1 by R the whole square plus 1 by omega L minus omega C the whole square. Now Y or admittance can be written in polar form as G plus JB, or in the R theta form as root over G square plus B square into tan inverse of B by G. So the cos phi value or the power factor value comes out to be G by Y. Hence phi is equal to cos inverse of G by Y, and tan phi comes out to be B by G. Hence phi comes out to be tan inverse of B by G. Hence the angle shown here is phi. Now let us study parallel resonance. In many ways the parallel resonance circuit is exactly the same as the series resonance circuit we have studied in the previous video, and the difference this time is that the parallel resonance circuit is influenced by the currents flowing through each parallel branch within the parallel LC tank circuit. Now a tank circuit is a parallel combination of L and C that is used in filter networks to either select or reject AC frequencies. Here we can see that, as we have already seen, Y is equal to 1 by Z, so Y would be root over G square plus B square, and inductance G is equal to 1 by R, so inductor susceptance is BL, which is given by 1 by 2 pi FL, and capacitor susceptance is BC, which is given by 2 pi FC. Now, a parallel circuit containing a resistance R, an inductance L, and a capacitance C will produce a parallel resonance circuit when the resultant current through the parallel combination is in phase with the supply voltage. So the corresponding instantaneous values of IL and IC will always be equal and opposite, and hence they'll cancel out each other. So we know from the previous series RLC resonance tutorial that resonance takes place when VL is equal to minus VC, and this situation occurs when the two reactances are equal, that is XL is equal to XC. Now Y is equal to G plus BL plus BC in vector form, so Y is equal to 1 by R plus 1 by J omega L plus 1 by J omega C, or Y is equal to 1 by R plus 1 by 2 pi FL or plus 2 pi FC. Now at resonance XL is equal to XC, so 2 pi FL is equal to 1 by 2 pi FC. Now F comes out to be, resonant frequency comes out to be 1 upon 2 pi root over LC in hertz, or omega R is equal to 1 by root LC in radian. You can see that the resonant frequency value is the same for series resonance and as it is for parallel resonance. Now at resonance, the impedance of the parallel circuit is at its maximum value and equal to the resistance of the circuit, since the LC circuit becomes an open circuit, the tank circuit becomes open, and at resonance I, that is the current, will be in phase with the supply voltage Vs. So the impedance is maximum at resonance, the impedance is inductive for frequencies lesser than the resonant frequency, and impedance is capacitive for frequencies greater than resonant frequency. Now we can see that the current is minimum at parallel resonant frequency since the impedance is maximum. Now the phase angle between the voltage and current of a parallel resonant circuit is 0 at resonant frequency point, since V, I and R are all in phase with each other. Now the quality factor Q for a parallel resonant circuit is given by R upon 2 pi FL, which is equal to 2 pi FCR, which comes out to be R root over C by L. We can see that the Q factor for a parallel resonance circuit is the inverse of the expression that we found and computed for a series resonance circuit. That's it for this video. Thank you.